Overview of Key Specifications, Chapter 3. Hello again. In this video, we'll provide an overview of the key topics surrounding redundant switch types and important system specifications in satellite communication. We'll walk you through some essential components and their role in maintaining reliable service. What's covered in this chapter? First, we'll dive into redundant switch types. Next, we'll take a closer look at system architecture, IFL cable, and the importance of a redundant power supply in keeping everything running smoothly. Then, we'll review a summary table that highlights the main specifications for each redundant switch device and explore each device further. Finally, we will look at the remote user interfaces, the switching modes, and IDU control. Now let's go over the key frequency bands commonly used in satellite communication. The S-band operates between 2 and 4 GHz. The C-band operates between 4 and 8 GHz. The X-band operates between 8 and 12 GHz. The Ku-band operates between 12 and 18 GHz. And we have the Ka-band, which operates between 27 and 40 GHz. The frequency band directly impacts the waveguide size, with higher frequencies requiring smaller waveguides. This, in turn, influences the size and configuration of the waveguide switch used in the redundant switch system. We have two different redundancy setups. In a one-to-one system, there is one active device and one standby device, so if the active device fails, the standby takes over. And in a one-to-two system, there are two active devices and one standby device for greater reliability in case either active devices fail. The RSW won't be able to support two active devices if two active devices fail. Let's explore the concepts of single-band and multi-band operation in redundant switch systems. First, we have single-band operation. Most devices operate on a single frequency range. Typically, the bandwidth is no larger than 2 GHz. A larger bandwidth can negatively affect parameters such as gain flatness, noise figure, and linearity. While single band simplifies the design and operation, it limits flexibility when a larger frequency range is required for various applications. To cover a larger bandwidth, we have multi-band operation. Some devices, particularly LNBs, can switch between multiple frequency bands, allowing a single device to operate across several bands. This switching is typically controlled by varying the input voltage and input tone frequency to the LNBs. For example, a quad-band LNB can switch between 4 bands within 10.70 to 12.75 GHz. The RF input frequency is usually wideband, and then the LNB downconvert a portion of the band within a 1 GHz bandwidth. These voltage and tone signals are provided by a universal LNB controller or ULC, which is built into the redundant switch controller box. The ULC ensures that the appropriate voltage and tone are applied to the LNB to switch between different frequency bands as needed. Now let's go over simultaneous band operation. In this configuration, the system is capable of receiving or transmitting signals across multiple frequency bands at the same time. This setup is particularly useful where it's necessary to operate across multiple bands concurrently to maximize data throughput. For example, for a dual simultaneous band LNB, the RF input frequency is a wideband range of 10.70 to 12.75 GHz. But the IF output frequency will be two narrower bands, typically within 1 GHz bandwidth. Unlike multi-band systems, which switch between bands, simultaneous band systems don't need to switch. They can handle multiple bands simultaneously with separate IF ports to the modem, offering greater flexibility and increased bandwidth. Let's now discuss the differences between RxTX systems and Rx-only systems in redundant switch configurations. RxTX systems are designed to handle both receiving and transmitting signals. To minimize the interference from the transmit signal on the receive signal, these systems typically include transmit reject filters, preventing potential interference or damage to sensitive receive equipment. On the other hand, Rx-only systems are designed solely for receive signals, so they do not include transmit reject filters. Alternatively, transmit reject filters may be sold separately and can be added to the system based on specific RxTX requirements. Now, let's discuss the two main configurations, ODU only and ODU with IDU. The outdoor unit or ODU only system is sometimes called a headless system. In the ODU only configuration, the entire system is an outdoor unit with no indoor unit. The ODU includes key components like the waveguide switch, controller box, and various internal system cables to manage the switching operations. The next configuration is the ODU with the indoor unit or IDU. In the ODU with IDU configuration, we have both outdoor and indoor units. The IDU is a 19-inch rack-mount controller that offers user control and system monitoring indoors, while the outdoor unit still handles the switching functions. As for accessories, both configurations require IFL cables for power, Ethernet, and the IF signal to connect the components to the modem and maintain communication between the ODU and IDU. Optional accessories include filters, input and output couplers, and lightning protection that can be provided depending on the requirements. When working with redundant switch systems, various cable types and connector standards are involved. Let's start with the typical cable lengths, which include 30, 50, and 100 meters options. These cables support monitoring and control with interfaces such as Ethernet, which can be used for HTTP or SNMP protocols. The ODU requires reliable AC power to ensure consistent operation. This ensures that all components of the ODU, including the waveguide switch, controller box, and the active RF components, remain operational. Next, we have the F cables, which typically come in either F connectors, N connectors, or SMA connectors, depending on your system's requirements. The AC power cable depends on the region of the end user. In a redundant switch system, cable length plays a crucial role in signal quality due to insertion loss. The longer the cable, the more signal degradation occurs. This is particularly critical for buck, block-up converter systems, where the modem needs to provide a strong enough input signal. If the insertion loss is too high, the buck may not receive sufficient power to achieve the desired output. For LNB systems, insertion loss is carefully designed to be below 20 dB, ensuring that received signals remain strong. LNA systems are usually paired with BDC systems. The LNA system should be installed close to the BDC system to reduce insertion loss. One important consideration is signal degradation for cables over 100 meters. In these cases, you might need to use a line amplifier or an Ethernet extender to maintain signal integrity over the longer distances. Ultimately, selecting the right cables and lengths is a balance between cost, installation ease, and minimizing the insertion loss to ensure reliable system performance. Some redundant switch systems have a dual AC power supply option. With dual AC inputs, power redundancy is fully integrated into one hardware controller box, meaning the system can keep running even if one power source fails. Another key benefit is load balancing. This distributes the electrical load between the two power supplies to reduce stress and extend their lifespan. Additionally, this provides maintenance flexibility. One power supply can be serviced or replaced without needing to shut down the entire system, ensuring maximum uptime. Lastly, note that an additional AC cable is required for the second power supply port. Let's take a look at the key specification of a redundant switch system. The insertion loss refers to the loss of signal power resulting from the insertion of a device in a transmission line. Typically, a redundant switch system is designed to have low insertion loss, ensuring that the signal attenuation is minimal as it passes through the redundant switch. Typical insertion loss for an LNB redundant switch is -2.8 dB maximum. The waveguide switching time refers to the time it takes for the system to switch from the active device to the standby device. In a redundant switch system, fast switching times are critical to ensure minimal interruption in communication. Typical waveguide switching time is 150 milliseconds maximum. Let's talk about the interfaces used in redundant switch systems. The redundant switch controller box comes with multiple interface options for connecting to other components in the communication chain. These typically include RF interfaces, such as waveguide or coaxial connectors, and control interfaces such as Ethernet or SNMP for remote monitoring and control. Next, let's discuss the 10 MHz reference signal and the different ways it can be configured in a redundant switch system. A 10 MHz reference is typically used to provide a stable frequency reference to devices such as LNBs or bucks, ensuring that signals are properly synchronized. If the device requires an external 10 MHz reference, there are three options for external reference. Via the redundant switch controller box, there is an external reference within the redundant switch controller box, which provides the 10 MHz reference signal to the devices. Via feed-through, the redundant switch controller box can accept an external 10 MHz signal from an external device through a dedicated 10 MHz reference port, which provides the 10 MHz reference signal to the devices. Via modem feed-through, the redundant switch controller box can accept an external 10 MHz signal from the modem directly via the IF cable. The 10 MHz reference will feed through the controller box to the devices. Here are the summary of configurations. Depending on the device, for example, LNA, BDC, LNB, or buck, there may be different configurations available. Here are the variety of options that Norsat currently offers, but you can request further customizations. Typical frequency bands that are covered are C-band, X-band, Ku-band, and Ka-band. We also offer S-band for the LNB. Usually, each device operates on a single frequency range. However, for LNBs and bucks, we support multi-band, and for LNBs, we support simultaneous band. Typically, we offer 1-to-1 and 1-to-2 systems. Some systems are TX-RX and offer a transmit reject filter. But if the system is RX only, transmit reject filters are not needed. Most redundant switches can produce or accept a 10 MHz reference, or have the device generate a 10 MHz reference internally. However, this is not applicable to an LNA because it does not have any frequency conversion. Typical IFL lengths are 30 meters, 50 meters, and 100 meters. Some systems will have an optional IDU, whereas some systems require an IDU to operate. For the LNB, we offer additional features such as a redundant power supply option and a boom mount option. Depending on the device, the input and output interface are typically a waveguide, N connector, F connector, or SMA connector. The low noise amplifier or LNA is responsible for amplifying the received signal from a satellite. The input of the LNA is typically a waveguide, and the output of the LNA is typically a coaxial connector such as an N or SMA connector. The LNA does not perform frequency conversion, which means the entire redundant switch system must support the high RF frequency. Switching between LNAs in a redundant system is typically triggered by a current fault, ensuring that a backup LNA is activated if the primary one fails. LNA redundant switch are typically combined with a BDC redundant switch to handle both amplification and frequency conversion. The BDC will convert the high-frequency signal to a lower frequency after the LNA has amplified it. The block down converter or BDC is used to down-convert the received signal from a high RF frequency to a lower IF. The input and output of the BDC is typically a coaxial connector such as an N, F, or SMA connector. Because the input is coaxial, the BDC typically uses a coaxial waveguide switch. The waveguide switch must be able to operate at the high RF frequency. Switching between BDCs in a redundant system is typically triggered by detecting a current fault. The BDC is often paired with an LNA redundant switch. The LNA amplifies the signal, and then the BDC handles the frequency conversion. This combination ensures that both signal amplification and frequency conversion are covered, providing seamless operation in satellite communication systems. The low-noise block-down converter or LNB is a device that amplifies the received signal and then converts the RF frequency down to the F frequency. The LNB combines the functionality of both an LNA and a BDC into one compact device. The LNB typically uses a waveguide for the input interface and a coaxial N connector or F connector for the output interface. The waveguide switch needs to support the high RF frequency, but after frequency conversion, the controller box only needs to support the lower IF frequency. LNBs come in a wide variety of options, including multi-band and simultaneous band configurations, providing flexibility for various communication needs. Bucks are equipped with monitoring and control or M and C interfaces. The block up converter or buck is responsible for upconverting the transmit signal from a lower IF frequency to a higher RF frequency and then amplifying it for transmission. The input interface is typically a coaxial connector, like an N connector or F connector, while the output interface is a waveguide. While the waveguide switch must support these high RF frequencies, the controller box only needs to support the lower IF frequency. Since bucks are generally larger than LNBs, the buck redundant switch will also be larger. This should be considered when installing the redundant switch in an antenna hub. On a buck redundant system, there is a load on the unused waveguide switch port. The load size matches the buck frequency and power. Bucks are equipped with monitoring and control or M and C interfaces, such as Ethernet, to allow for remote monitoring and fault detection. Switching between bucks in a redundant system is typically triggered by an M and C fault, ensuring that a backup buck takes over when issues are detected. There are two main operational modes for bucks. Eco mode reduces power consumption by muting the standby buck while it is not in use. If a fault is detected, the buck will switch immediately. However, the buck may need time to warm up and the power may fluctuate before the gain of the newly active buck stabilizes. Hot standby mode keeps both the active and standby bucks powered, allowing for immediate switching in case of failure. The redundancy switch controller maintains the gain for both bucks. The redundant switch systems offer remote user interfaces for setup, monitoring, and control via Ethernet. The Ethernet M&C can be controlled via 1. Via web page or SNMP using the ODU and/or the IDU. 2. Via the IDU front panel. Settings that can be configured includes Device Info, which provides detailed information about the device used in the redundant switch system and includes the fault status. Device Setting, where users can set redundant switch-specific settings and adjust fault thresholds. Network Settings, which allows network configuration to ensure the system is connected and remotely accessible, and Firmware Update, which allows the user to upload the most recent firmware file. Now, let's talk about the different switching modes and how the IDU can be controlled. There are two main operation modes for the redundant switch system: automatic mode and manual override mode. In automatic mode, the system automatically switches from the active device to the standby device if a fault is detected. This ensures that there is minimal downtime in case of a failure. In manual override mode, the system doesn't switch based on faults. Instead, the user has full control over which device is active at any given time, regardless of whether there is a fault or not. This is useful for maintenance and testing purposes. Users can easily switch between modes and control the overall operation of the system.